Hello, and welcome to the second in the Reigate Maths series for the second year Decision 1 content for the Further Math A-Level, focusing on the Travelling Salesman Problem topic. In this video, what we're going to be looking at is finding an upper bound using the minimum spanning tree method. In this A-Level, you will learn two methods. This is the first of them. As I said in my introduction video, we are going to be using the same network for all of the different methods. The two methods that we'll use to find an upper bound, and then the singular method that we'll use to find a lower bound. The first method that we're going to look at today is called the minimum spanning tree method, and this finds an upper bound. Now remember, an upper bound is all about finding correct answers. So this is important about the upper bound. Upper bounds always form TORs. That's the point of them. They are valid answers. Now, obviously, in order to find the best answer, we could just find every single TOR that exists in this network, but that is not feasible to do. If you are particularly interested, it's not on the specification, but the number of correct TORs for this is n-1 factorial over 2. So we've got 8 vertices, so we do 7 factorial divided by 2, which is going to be a very large number. So it's not really feasible to try and find every single TOR. So this finds a good one. This is a little bit of a longer question than the other method for finding an upper bound, but it's quite a nice one because it means that you can do more things in a question, because the first part is finding a minimum spanning tree. This is using Prim's or Kruskal's algorithm to find a minimum spanning tree. What you then do, because the answer that we're trying to find, we need it to be a TOR, or a cycle, we take our minimum spanning tree and we double it. So what that means is we start at, say, A, we go over every arc and get to H, for instance. We then double the minimum spanning tree to get back using exactly the same path from H to A. Now obviously this is going to be quite a large upper bound and we want to find small upper bounds. So what we then do is just by looking at it, we find shortcuts. Typically in an exam question, this topic will be broken up into a couple of bits, and one of the parts will say, okay, find a minimum spanning tree, use this to find an initial upper bound, and then hence, by using shortcuts, find an upper bound that is below, and then they'll give you a certain value. Not always, but sometimes. And that's kind of this method. But first things first, we need a minimum spanning tree. So I'd like you to pause the video now and use your preferred method of Prim's or Kruskal's to find a minimum spanning tree for this network. So you can see here, I decided to use Prim's starting at A to find my minimum spanning tree. If you use Kruskal's or Prim's starting at a different point, you should get the same final answer and final length, just the order of selection might be slightly different. That's fine. In an exam, if they really care, they will tell you what order to do it in, or which one to do. So I've written the length of my minimum spanning tree here. What I didn't mention before is the units of everything here are in miles. So we're going to put that. Obviously, if it's doesn't have a unit, then you don't put one, but it very typically will. So this is step 1. Usually, if they want you to do this method, this will be part A. Step 2 is finding our initial upper bound. And we do this by taking the length of our minimum spanning tree and timesing it by 2. What this effectively allows us to do is if we start at C, we go from C to A, then we go from A to B and then back again. Then we go from A to E to H to F to G to D and then back again. And we get back to C. And you can see we've traversed every single arc of our minimum spanning tree twice, hence doubling the initial upper bound. For this last step, step 3, it's very useful for us to have this diagram. So make sure you've got this drawn. Because what we're going to do is we're going to find shortcuts. Now, often in the exam, they will tell you what number you're aiming for. And for the purposes of this example, we're going to look to use shortcuts to find an upper bound that's less than 1,260 miles. They might give you a different number, that's fine. So, what we can think about, and we can look at our diagram and use this to figure out, well, if we look, we've gone all the way from A to D and then back again along every single arc. Well, one shortcut we could use is we could go straight back from A to D. So if we go from A to D, that's going to remove this amount from our initial upper bound. So shortcut A to D. It's going to give us a length of 1,502 minus all of these added together, but then we've also got to add on that A to D length here, the 382. So we now have another upper bound that's going to save us some time. With a quick calculation, we can see that this gives us 1,264 miles. So slightly short, or slightly too long, for the target of 1260. So we need to find some more shortcuts. Well, if we look and see, okay, we're now also repeating B to C a lot. So if we go straight from B to C, instead of going back through A, that's another shortcut. So we've got this 1,264 minus the repeated length of B to C plus the length of B to C, which is 121. Which then gets us down below this 1,260 miles that we're looking for. So this is our improved upper bound, and you can see it's a vast improvement. You know, we've saved 250 miles almost off what our initial upper bound was by just making two shortcuts. Now, we didn't have to make those two. We could have done shortcuts here and maybe here, and that could have worked. So you might get slightly different answers depending on which shortcuts you take. But as long as your answer dips below the target number and you justify it correctly, that's good enough. Now, in terms of working, you need to really make sure that it's clear why you're subtracting this total, or that you're subtracting this total. Don't just put, okay, it's 1,502 minus, and then whatever all these added together are, plus 382, because that's not clear enough in terms of working. Make sure you lay out your working like this. Now, depending on the textbook you use, the examples might justify it in a slightly different way. What they may do is they say shortcut A to D is this, so it saves us however many miles, 238 miles, and then do 1,502 minus 238 to get this 1264. Either way, it's doing the same maths, just writing it down in a different way. But that is the first of the two methods to find an upper bound for the travelling salesman problem. In the next video, we're going to look at the other method, which is using something called the nearest neighbour algorithm. Thank you for watching.